Just so they at least got a little something here. All right, 1 BTU. So 1 BTU is equivalent to what? How many joules? If one quad is 1 times 10 to the 18th joules, which is 1 times 10 to the 15th BTUs,
1 times 10 to the third.
yes.
No, no,
I don't know, Liz, I was talking inside here.
that's totally the same. What?
Good job, Liz.
That is
1,055 joules. All right. Oh, and one more. Sorry, there's another unit here. Equal to 1 exact exajoule. Sorry, exajoule. 1 capital E capital J. 1 exajoule. EXA joule. Exajoule. That was new to me. I didn't.
Why do you have exajoules and quads if they're equal?
It's the same thing. Yeah, I just gave you another unit. I'm just throwing all these terms out. I think it's good when you're doing readings like an article, or if you get an authentic reading on the AP test. That's the thing you're gonna have to do, multiple choice or a short answer. They're going to give you an article, a journal, whatever. Could be a something from a newspaper, who knows. And if they're using terminology and units, I don't want you to read a unit on the test for the first time, right? So I'm trying to just give you as much as I can, even if you don't remember all of it. At least you're exposed to it, because these you've heard of, but maybe not a quad or BTU or exajoule, right? So those are the unique to this class. So British thermal unit is the amount of energy needed to raise 1 pound of water 1 degree Fahrenheit. Since it's British, they're talking pounds and Fahrenheit. Everyone else uses kilograms and Celsius, for example. So 1 pound of water 1 degree Fahrenheit, that's a BTU, a British thermal unit. What else do I have here? All right, I'm gonna clear this. So a watt is 1 joule per second. 1 watt is 1 joule per second. So if you want to run a light bulb that is a 1 watt light bulb for 1 second, that's 1 joule equivalent of energy.
Did you need to say a pound of water?
Yeah, it's Brit. That's how they talk.
But like they don't use
Like money?
ounces.
So
Only
no,
America uses ounces.
Britain uses pounds. Like a pound
For
is like
everything,
money or whatever, like a pound, right? Don't they use that term?
Yeah.
Yeah. All right. Also, for fans of physics here, watts is equal to amps times volts. And a volt, hold on, they're all connected. We'll leave it at that. I don't need to get into all that. 1 kilowatt hour. 1 kilowatt hour, which is what will be on those electric bills. Did you guys look into that yet? Try and get that soon, so we can look at that. The electric bill is really more I care about than the heating. I mean, if you heat your house with wood, you don't have a heating bill anyway. So get your electric bill. Kilowatt hour. 1 kilowatt hour is equal to 3.6 megajoules.
Making up words.
When do you want those electric bills back?
As soon as possible.
Alright, just bring them in.
Yeah, bring them in. Making up megajoule. I'm not making up megajoules. Mega's a unit. It's a power of.
10.
No.
It's
Pi.
10 to the what?
6.
6.
Okay.
So 3.6 times 10 to the 6 joules. 3.6 times 10 to the 6 joules. Now, here, for kilowatt hour, make sure I want you to write this down. The amount of energy in kilowatts, what's kilo mean? 1,000. So the amount of energy in kilowatts needed to run something, think of something, light bulb, refrigerator, whatever, for 1 hour. So it's the amount of energy in so that's literally what that means. The amount of energy in kilowatts needed to run something that's plugged into, an outlet or something that has electricity for 1 hour. The amount of energy in kilowatts needed to run something on electricity for 1 hour. So when we'll dissect the electrical bills and we'll talk more about that down the road. All But the amount of energy in kilowatts needs to run something on electricity for 1 hour. So would you expect more kilowatts needed for a refrigerator or a light bulb? Right, I mean, you guys already kind of have a concept of, I need more energy for this, less energy for this, but anyways, we'll talk more about it. Okay, here we go. So that's some of the terms and units that I wanted to talk about. Why are LEDs so much more efficient than regular light bulbs?
They don't give off heat.
They don't give off as much heat. What else? They use less. Right. So if you have a 60-watt light bulb, an LED equivalent might use 7 watts. Produce the same amount of energy, lights.
How? When's that possible?
Way more efficient. Fluorescence and incandescent, old ones with the filament, those rely on basically just heating up a piece of metal till it glows. So you're losing all types of energy to heat. Fluorescents are a little better. You're exciting electrons and gases, but there's still heat associated with that. LED is more like semiconductors we learned in AP Chem, where you have these metals that are close enough where it gets pretty confusing. You have conduction bands and what's the other band? Electrons are jumping up and falling, releasing energy, but it's very efficient how it does that. It's very hard to just explain. I'd have to show you and draw it, but very different than the other forms of light. So it can use less energy and produce the same amount of light. That's why they're so much better. All right, let me show you this, some slides here on energy, world energy consumption. Here.
She's got school. She's got school.
What?
Sorry, I didn't have this ready.
Oh yeah, you schooled me on
Poor planning here.
You would have told me that. That's 5 words.
What chapter was the fossil fuels in?
Yeah, what is the
For,
word? What is the
10
word?
or 12.
Yeah, we
Stop talking about orifices.
He's got an orifice in his shirt.
Where?
Where?
Where? You guys
I want this shirt.
Ah, I'll pull it over to your thumb. There. Uh-huh. Yeah, that's.
Here we go.
Worse.
Oh, wait, what?
Still not wearing a shirt.
I would. I'm mad at him.
Oh.
It's a joke.
You thought too hard about that. You're right. That's I know you sat up there concentrating, counting. To then
Boy, I asked my mom if I could bring in the energy bill. She goes, odd, but okay.
Did you tell her why?
I said, well, Koi wants us to bring in our energy bill, or electric bill. And she said, odd. And I said, we're doing it for an energy unit. She goes, okay, that's fine.
Okay, good. All right, here we go.
We were just talking like that.
Stop doing that. All right, here we go. We already talked about fossil fuels, non-renewable, nuclear fuel. We can skip all that. Why don't you write these percentages down? Worldwide pattern of use of 2015, here we go. We got 22% natural gas, 28% coal and peat. Peat is a precursor to coal. So it's plant remains that are starting to decompose, but it's not even close to being coal. All right, I mean, peat you can harvest, like we said in that one worksheet, you know, just a couple years of growth, let's say, or a couple years of decomposition. We're not talking 300 million years. And then oil. So as you can see, 81% of the fuel here on this chart, fossil fuel for energy. Renewable, 14, nuclear, 5. Oh, there you go, there's those units, 570 exajoules. That's 540 quadrillion BTUs, or quads, per year.
Quadrillion, that's a lot.
Wouldn't peat be in the same category as like a biofuel?
Yeah, it could be.
Why did they pack it with coal?
Yeah, it's not a fossil fuel, right? So you shouldn't. It isn't a fossil fuel. So yeah, you're not wrong. But they're just lumping it in because it's a precursor.
Can you not read? Why not? Can you just tell me what? Yeah, it's 14.
Um, So fossil fuel use is actually increasing. Why? In the world?
More cars and stuff.
More car.
Keep
Okay.
that trick down.
Countries are becoming
Affluent.
more developed, right? So if you need to write that down, then write it down. If not, then you don't have to. But as developing countries become more developed, what's that called? As the stages? Right. What's that whole transition called? That's the second word.
Demographic.
Demographic, right. So as we're shifting through the stages, demographic transition,
You said that so fast.
sorry. As we're shifting, some of the developing are becoming more developed, and therefore their energy needs, because they're living more like, let's say, us. So fossil fuel use is going up. If you look at this here, this is in exajoules. China, United States are the two highest. And per capita, what's that mean?
Per person.
Per person, annual energy consumption. So even though China's overall consumption is really high, why is that?
A lot of
A
people.
lot of people, look at their per capita compared to us, right? So we have less people, but each person here is using more energy. That's the takeaway from that one. Why? The United States is developed, China's developing, and not everything is. So our country, if you go to any state, any part of our country, energy is fairly evenly distributed. Yes, people with more money have more access to energy, people with less money. That goes for all across the world, but it's more evenly distributed here in the United States, for example, than let's say China. So that is another thing that I wrote down that I want you to understand. The use of energy resources is not evenly distributed between developed and developing countries. That's what I'm trying to show you here. So again, you might want to write that down. Energy resources not evenly distributed between developed and developing countries. Primarily developed countries have more urban environments, cities, whereas developing countries are more rural. Yes, there's some enormous countries in China, but there's a ton of rural areas in China as well. As far as state, like area, there's a lot more rural. So again, the energy resource is not evenly distributed. Think more urban with developed, more rural with developing. And if you have more urban, so think United States, then you're going to have a lot more fossil fuel use, more energy use. Look at Chile. That's interesting. Hardly anything here. It's just interesting to look at that.
Nothing to eat.
Yeah. Okay. So you don't have to write this down. Just commercial means it's bought and sold, and then subsistence energy is gathered by individuals for their own immediate needs. So, does anyone chop down their own wood and burn it for their own heat?
I mean, that's like
Sometimes.
Right. So that's
half
that.
the reason.
Okay. You chopping down wood and selling to other people?
No.
Well, that would be that, right? So commercial energy. So like I use commercial energy sources. I have natural gas. I'm not getting that myself. But if you're using your own wood, doing it yourself, that's subsistence energy source. So if you were to guess which one is more towards developed nations versus developing, which one's which?
Commercial.
Right. This is more for developed. This is more for developing. So if you're in a developing country and you're in the middle of nowhere, the nearest city is like whatever, hundreds of miles. What are you gonna do for energy?
Down the trees.
You got to use things around you, right? So that's what that means. Okay. My brother-in-law and his wife. So my wife's brother, her and his husband. My wife's brother and his wife both were in the Peace Corps, and they went to Madagascar in their like early 20s. They spent a good deal of time there. They and there's a lot of poverty in rural areas in Madagascar, and they helped them actually build. They're called dung ovens. So you use dry manure and make ovens out of it, and then they use those ovens to like cook and stuff.
Yeah,
Wait,
because
one
I
more
want
time?
to cook my food in something made out
It's
of animal
it's just the
feces.
casing, so it's to protect it, and once it's dry, it actually works well. They
It's a
say.
little sketchy.
Yeah, well, again, they're using what they can, right? So
Material-wise.
what's their carbon footprint using that?
Very low.
Zero, basically. You know,
Is
so.
that- Wait, isn't that for like methane in their food? Like, cause if you're burning. their
No,
food-
because they're not burning the, well, okay, yes. If you heat up waste and manure, yes, you're gonna be producing stuff. Right. But it's pretty low level.
So
I mean,
it
we're not
doesn't
talking
get
millions
into
of
their
people
food?
here. Well,
It doesn't get into their food.
it might, yeah, it might. I mean,
Ew.
they kinda don't have an option.
Right.
It's pretty poor. So, they also explained, 'cause I talked to them about heat, like where they get heat from. He said, they both told me primarily wood, listen up guys, primarily wood and charcoal. How do you make charcoal? The right way to make charcoal, like really good charcoal, is you burn wood with almost no oxygen in the environment. So
But
what would that cause the wood to do?
smolder. But
Burn, but not very fast, not very hot. Well, it could
But
be
there
hot,
has to
but-
be some oxygen.
You need a little
because it
bit,
won't
right? But the
burn
way
out.
to make charcoal, and I asked them, and he said they had these like, essentially like almost like these pits dug into the ground, these boxes, and they stuffed it with wood. They lit it on fire and then sealed it, and then it would burn for a long time, and then eventually it would burn out. And when they opened it up, they had really good charcoal, and that charcoal is very dense because wood. What does wood have in it that isn't good to burn?
Water.
Water. Good. It dries off the water.
But why don't they?
And there's other volatile compounds in it. If you keep it contained, that's where the charcoal retains its energy content. If you just burn wood like in an open, like on the floor here, you get charcoal, but it's not the same consistency and it's different composition. Plus it burns differently with all that oxygen. The chemical reactions change. So when you have it under low oxygen, you can get really good charcoal. I'm trying to just get you to understand, I'm not doing that at my house, right? I'm just using natural gas from the city, so that's the big difference there, right? Big difference. So, interesting. Pretty cool. So if you look at that, it's just going up, up, and up. All of it is going up. More people, and then more developed nations. Let's see, what's this one here? Oh, this is good. Let's write this down. I'll give you the percentage here. Shows United States consumption and then the sectors. So this is the U.S. consumption. Let's write these down. So U.S. consumption 2016. Oil 37%. This is contradicting what I wrote down. Hold on, hold on. I like these numbers better. We'll go with these. Oil 37%.
That's not how numbers
Kind of. Anybody who presents any statistics, it's usually using numbers that favors their argument, even though they could be factual. Natural gas 29%. So oil 37, natural gas 29, coal 15. Oil 37, natural gas. Can any of you read those numbers?
No.
Oil 37, natural 29, coal 15, renewable 10, nuclear 9. So that's US 2016. And part B here, this one. Industrial, 32%. So what are we using the energy for? Industrial, 32%. What's that?
Factories.
Yeah, businesses, factories, schools. So that makes sense, 32%. Transportation is close, 28%, also makes sense. A lot of cars, 28%. So industrial 32, transportation 28, residential next with 21%. I'm sorry, I misspoke. Commercial is 19%. That's businesses and schools. What's industrial? that's more factories and that nature. I kind of grouped them together, sorry. Commercial is businesses and schools, for example. So 32 industrial, 28 transportation, 21 residential, 19 commercial. Do I expect you to memorize all these numbers? No. Just trying to put in perspective. Here's what we're using for energy. Here's how we're using it. That changes depending on the country and how many people, obviously. Here we go. This thing here. Energy, E-R-O-E-I, energy obtained from fuel divided by energy invested. Just write that one down right there. This actually I don't think is even in the curriculum, but I found it interesting. So we'll talk about it real briefly here. So the energy obtained from the fuel, let's pick a unit, BTUs or joules, whatever. Energy invested to obtain the fuel. So if you take the energy you get from the fuel, divide it by the energy needed to obtain it, of course that's going to be how efficient it is. The larger the value, the more efficient. So the harder it is to get the fuel. So if you want to do subsurface mining to get anthracite, the best coal, which tends to be deeper, that's going to take a lot of energy to go into that. These calculations are not simple, and make it sound simple, but to calculate all the energy going into that fuel, we're talking labor, we're talking machines, we're talking lots of things, right? So anyways, the point of that is making sure you understand the efficiency is basically what's the net you're getting from that. Okay. Yeah, all right, just real quick here. So you take the energy resource from the ground, you gotta extract it, you gotta move it around, you gotta process it. Can you take crude oil out of the ground, pump it in your car?
No.
No, what do you have to do to it?
Process.
Right, you refine it into gasoline, right? So there's that. The combustion energy or conversion, right? Turning it into whatever it is, electricity or heat. There's waste transportation involved with that, and then we're gonna use it. So there's a lot that's going on. The red arrows, what do you think those mean?
Energy loss.
Energy loss.
It says right there in the
Yeah.
center.
Well, I'm not sure you can read that, so. Yeah, second law of thermodynamics says, if you transfer energy from here to here, is it gonna be the same amount? No, you're gonna lose it throughout, through that process. Give me a couple more minutes.
We got.
We got 1.5.
Actually,
We can stop. I feel the energy sucked out of us.
What? Wait, what? I didn't hear you say.
Good.
It's not good. What is your funny story?